So partial fraction, what is it? Partial fraction is when you take a rational function, some polynomial over some polynomial, and you break it into basically primes of that polynomial. So if I were to factor this guy, I would get x minus 1 and x squared plus 4. And I know that it's going to be some number over this guy and some polynomial over this guy, and so I break it up. This is going to help you in calculus, really. You're going to use this for integration, which means probably not much to you right now, but this process is something that will help you when you start doing some more functions. Knowing how to split it up into more simple pieces or more prime pieces helps you then do another process that you need to do that would be much more difficult to try to do it here. These are much easier to do that particular process with. So this is kind of a stepping stone so that you have this in your back pocket as one of your options when you get to other maths where you need them in smaller form. So find the partial fraction decomposition. The first thing we're going to do is we're going to factor this denominator, okay? And that tells us how many pieces we're going to have. This is a pretty basic one to factor. If I were to take this, I'm looking for factors of 8 that subtract to give me negative 2, which is going to be x minus 4 and x plus 2. So I know that I'm going to break this up into an x minus 4 and an x plus 2. Some number at the top that I don't yet know will be there, okay? And that's going to equal my original problem. So the whole process here is to kind of ignore this for right now and to get these with a common denominator, okay? Which means this is going to be the a times what it's missing plus the b times what it is missing. We know the common denominator is that. We just need to know what the numerator looks like. We're going to simplify this. So we have ax plus 2a plus bx minus 4b. And we kind of group these guys by what they are. So my x's, those are my coefficients of my x. The coefficients of my x's are a plus b. So those should equal, so this is my numerator. Those should equal the coefficient of my x here. And then I do the same thing with my constants. My constants that don't have a variable, 2a and negative 4b. And those should equal my constant here. There's a couple ways you can do this. You now have a plethora of ways to solve linear sets of linears, right? You can solve by elimination, you can solve by substitution, you can solve by matrices, right? If you get really good at matrix and plugging those in, you could do Kramer's rule, you can do augmented. I'm sure that's how everyone is going to choose to do it, augmented matrix. But you can solve it any method you want. I am not going to force you to use matrix, even though this is the matrix particular chapter. There are going to be times when it's big, and I'm going to show you in your calculator how to then use a matrix. But for something like this, it would take me longer to put it in my calculator than it would for me to do elimination, to be honest. So I'm probably going to do elimination here. I can literally just divide everything by negative 2, right? Get negative 1, get positive 2, get negative 5, right? And I'm there. So you can solve it any method that you want. I honestly am not going to make you do one way or the other. When you do this guy, you get 3b equals negative 3b equals negative 1. And like anything else, you can plug it back in and you'll see that a equals 3. So your final answer is not that. Your final answer is to take these and plug it back into this guy. So your final answer, if I were to break this up or decompose it, it would be my a, 3, over this x minus 4. And since it's a negative 1, I'm just going to say minus 1 over this x plus 2. That is the partial fraction decomposition of that particular problem. This is something that we don't think about, but you have to account for every factor. And if it's a repeated factor, you have to account for the fact that happens once, twice, three times, like in this case. This is technically x plus a cubed. So we have to say we have a potential a over it to the first power, to the second power, to the third power. You've got to do that factor for every option up to the highest exponent that it is used. Okay? So like if I were to do this guy right here and factor it, take out an x, you get x squared minus 4x plus 4. That's actually going to be x minus 2 quantity squared. So that means I have to set up 3 here. I have to set up an a over the x, which is a factor, a b over the x minus 2 to the first power, and a c over the x minus 2 to the second power. Okay? So then I have to multiply the pieces by everything that they're missing. So like the a is going to be multiplied by the x minus 2 squared, right? Because that's what it's missing from this. The b is going to be multiplied by an x and 1x minus 2, because that's what that one is missing. And the c is just going to be multiplied by an x. So you have to think about what would I do if I were having to truly add these up. I would multiply each numerator by whatever it's missing from the common denominator, which is this guy in factored form, right? And then you just multiply. So this is going to be ax squared minus 4ax plus 4a plus bx squared minus 2bx plus cx. Right? I think I did that correctly. So now what I'm going to do is, so this should all equal my numerator. I'm going to pull my x squared. So I have a and b as my coefficients for x squared. So that should equal my coefficient for my x squared. For just my x, I have negative 4a as a coefficient. I have negative 2b as a coefficient. And I have positive c as a coefficient. And those should all equal the coefficient of my x, negative 21. My constant is the easiest. 4a should equal my constant, which is 16. All right. So here's the thing. Again, often in the book, they're going to tell you to use like a matrix here. I wouldn't use a matrix. What do you think I would do here? Solve for a. I mean, that's what I would do. A is going to obviously equal 4. Then you can plug it back in here. So my b is going to equal 3. And then I can plug it in here, and my c is going to equal, I think, 1. Yeah. No? 1? Yes? Yeah, it's 1. Question. So once you backfill those, which is how I would solve this and plug it in, again, your final answer is going to be what happens when you put those there. All right, so I'm going to say it's going to be 4 over x plus 3 over x minus 2 plus 1 over x minus 2 squared. That is my answer. Irreducible quadratic factors. Quadratic, you should know that term. Degree of, there we go, degree of 2 parabolas. So there can be a case where maybe your quadratic doesn't reduce at all. So that just means it's part of your common denominator, okay? If that happens, then you have a linear in the denominator, a constant on the top. A quadratic in the denominator, a linear on the top, all right? So you're always 1 degree lower, if you'll notice. So I have an x plus a, that's just a constant, degree of 1. I have an x squared plus bx plus c, that's a quadratic, degree of 2. On the top, I have a bx plus c, okay? So that's what we're going to do when we start setting these up. And then your denominator is just going to be what it is, you know, and then you're going to have to use some method to solve. So for this one, one thing you have to recall is how do I factor perfect cubes? Hopefully we all remember that. My factoring of a perfect cube is going to be a plus b, a squared plus ab plus b squared. Hopefully, or minus, sorry. This guy's minus if that's plus. So if it were minus, it would be minus plus. Plus is plus minus, but you have to remember this. And by the way, when it is a perfect cube, this little guy is never going to be factorable. Never, okay? So anytime you have perfect cubes, you automatically know that this trinomial is not factorable. It never is. So I'm going to have to set up an a over my x plus 1 and a bx plus c over this non-factorable quadratic there. All right? Which means this whole thing is my common denominator. So I'm going to say, well, I have to do a times this quadratic. And I have to do bx plus c times the x plus 1. All right? And then we're just going to simplify these, distribute. So I have ax squared minus ax plus 1. Foil here. So I have bx squared plus bx plus cx plus c. And then I'm going to do the same thing I did before. I'm going to pull the different pieces. So I have an x squared. Well, my coefficients for x squared are a plus b. Those should equal my coefficient of my x squared, which is 5. I have just an x. So I have negative a, positive b, positive c, and that should equal my coefficient here. And then I have, oh, that should be an a. I said a, I just didn't write it. That's an a. My constants are a plus c, and that should equal my constant here. I wrote 5. That's funny. This is a and b. Helps to write it what you're saying. All right, so again, they actually show you how to do this in your calculator. If this were like 3, 3, and 3, I would probably do it in my calculator. Okay, so let's say I had ABC, ABC, ABC on all of these, which is possible. Then I may do this method. I'm going to show you the calculator features. If I wanted to do this in my calculator, I'm going to set up a matrix that is not a 3 by 3. It is a 3 rows by 4 columns. Okay, so you'll see that they input into the matrix function the coefficient and the answers, right? So they have 1, 1, 0, 5, 1, 1, 0 for C, 5. Negative 1, 1, 1, negative 4. That's this guy. 1, 0, 1, negative 3. That's that guy. Okay, so they input this into the calculator as a matrix. And then this is one of your options under the math piece of your matrix. So if you go into the math portion of your matrix menu, you'll see this little guy. You input him, he opens, you go back to your matrix menu and choose the one that you plugged in, hit enter, and voila, you have your augmented matrix. Yeah, it does it for you. All right, here's the thing. If it was like this with these tiny numbers, by the time I went to my matrix and did all that, I could have canceled out. a B or a C from this guy and solve by elimination, right? So if I have numbers this small and it's ones and negative ones, I'm probably gonna calculate it before you can get it into your calculator. Okay, so again, you are welcome to do this. If you do this piece of it, I need you to set up the augmented matrix on your paper. Meaning, if you use your calculator, that's perfectly fine. I need to see that you set this up on your paper, okay? And then plugged it in. Otherwise, I personally would solve this guy by elimination. Like, I would take either the A plus B and cancel out something here, right? If you were adding these together, then you'd have a B and C and a B and C, all right? And you would be fine, all right? So I would do one or the other. I would cancel or elimination is probably how I would solve this, because I could very quickly solve this by elimination. All right, so if I eliminated this, I would add these two guys, right? The A's would cancel, B plus B would be 2B, and I have a C that doesn't add to anything, and then a 1 with a 5 and the negative 4. And then I would add these two. A and A cancel. I have 1B, 2 C's, and a negative 7. And then just multiply whichever one you want. Like, so if I multiply this by negative 2, it would look something like that. Once I have him, I have the rest of them, right? So B is going to be 3. A is going to be 2. If I plug it in here, that'll give me an A of 2. And then if I plug in a 2 down here, that'll give me a B of negative 5. I mean a C, sorry, of negative 5. So I have my A, my B, and my C. And then you literally just plug it back in. A, that's 2 over x plus 1 plus bx. So that's 3x plus C, but C is a negative, over x squared minus x plus 1. I just thought this was an interesting piece here where systems of equations were originally solved using base 10 systems with counting boards, which led to the abacus, which is really a cool way of multiplication and everything else. But we have certain ones that represent ones, tens, hundreds, and your places. And you may remember these from elementary school. If you look at the next page, you will see that they have kind of a breakdown of your decomposition. Distinct linear factors will break down to just your constants. When you start having repeated factors, don't forget that you have to do it for every exponent up to the highest exponent that was used. If you cannot reduce your quadratics, you will have a constant over linear, you will have a linear over quadratic. And then as that goes up, irreducible quadratics, you have to do the same thing with your quadratics that you did with irreducible linears. If you have a quadratic that is to a power, you have to do that to the first power, to the second power, up to the highest power that the quadratic was used as well.